So back to Fortran, and we were at the point where things are getting interesting as we'll move from a quite poor performance to a better one. So maybe some advice for people who have problem with the image. As you are the user Jovian, if you cannot modify your code in the where it is in the image, please copy it to the /tmp so that we can move. Yes, the example folder, please copy it to /tmp, and from there you.
Okay.
Anybody succeeded in compiling the proposal? What about performance? Okay, so we look directly to the CMake file itself. And the first reason why it is so slow is that we have been compiling in debug mode. So it was a trap. Okay. So sorry, I'm building some image again. Sure. So when compiling without the debug options, but in the release mode, do you find some improvement?
Yes, I have an improvement of factor 4.
We're on the right way. So now we want to use OpenMP to use multiple thread. So you have seen the OpenMP state directives that were sparsely distributed, randomly distributed in the source code. Why are they not in the right place? So this is indeed a parallel region that we have delimited. Here and here, but this loop is an iteration, and so will not distribute this loop over thread. Will distribute what is inside the loop. Okay, so what we have here is we hope that the compiler will discover that this function that evaluates the Laplacian, and then this array expression that put the result of u1, u0 plus the time step on the second, the right-hand side of the equation, build u1, and then copy back u1 to u0 and v1 to v0. We hope that, given that this inside the loop is parallel, the compiler will discover the loops inside the function and inside the implicit expression to provide us with a parallel result. It's a bold move. Will it work?
Sorry, what are the differences between the CMake list with OpenMP?
So let us show this. Okay, so not this one. Okay, so now in the what we have taken from the CMake list.openmp from the solution is we require OpenMP to be taken into account. We use it in the target link library. This should lead the compiler to use the options as well. Does it answer your question? Ça marche pas? It doesn't work?
Oh, sorry.
You see, the difference is here. Not only we have the HDF5, but also the OpenMP. package is required. Okay. So yes, my take at CMake was a bit naive. Maybe it's not enough to comment the debug statement. So if you pass the CMake build type option set to release when launching your CMake, not so much. Doesn't look good. Okay. So here we have the release option that has been taken into account over there. We have checked that we have the proper values for the parameter, including the number of steps, only 300. And the compilation has been done with and now we have to take the OpenMP into account. Okay, sorry. Okay, we have a compilation with OpenMP. So this is the point for discussing the intermediate result. We see that the real time here is 8 seconds, but the user time is 5 minutes. So this is surprising at first, but it means that the real time is the whole clock time, the one that you measure. On some multi-threading had been at play, which makes the user time much longer than the whole clock time because multiple threads are spending time, not so efficiently. So this is the next step, and this was the idea of the idea at play when we want to OpenMPify some code.
Sorry, just have a question.
Yes.
So I have the same feature as you with the user time, which is very huge, but with OpenMP, it's like 3 times slower than without in my case, which is a bit surprising.
So you mean the user time is even bigger than before?
Yes, but my real time as well. So because before I had like 0.1
Yes.
1 second, and now it's 0. No, sorry. Before it was 1.5 seconds, and now it's like 5 seconds.
Yes.
With OpenMP.
So this points out the problem we were looking at first. Okay. Life is not so easy as to sprinkle OMP directive this way. Somehow, Fortran misses its vocation. We would like to provide a formula, such as this formula, which are compact and elegant, and let the compiler do the work. No, not this way. So usually we have OpenMP parallel do. Okay, it should not apply to this kind of do loop because this one is really some iteration and not some enuplication. And the aspects of modern Fortran are nice in the sense that we avoid to look at what happens here in the function or here. What this array expression tells us is there must be a pair of loops over the indices of U1 and U0, as well as the Laplacian of U, which is an array as well. So all these parameters, all these variables have indices. In old Fortran, we would have explained all the loops explicitly. And we would have put the OpenMP do on both sides of each of those loops. So we are very dissatisfied with this. It will have us write a lot of ugly code. We will increase the number of loops, of indices. The expression will be longer. And this is not really what was the promise of Fortran. So next time, when we'll be using the NVFortran environment, we'll see what Fortran can do with do concurrent loops and auto-parallelize it. As was discussed in the last ORAP conference in May, some people have been writing converter programs that will rewrite your modern Fortran into old Fortran in order to ease the use of OpenMP. We would like a much better solution. Function Okay. In this function, we see we provide the stencil, which is in fact a constant. It's a parameter array. And we loop very naively on each value of the indices for the array from which we want to extract the Laplacian, plus we loop over the indices for the stencil. And you can see that contrarily to a popular belief, indices in Fortran can start wherever you want, not only from 1. So here the stencil is declared to go between -1 and +1. Okay, so in this kind of loop, we want that in order for OpenMP to do something useful, we want the loop to, we want to distribute the two loops over I and j among threads. So the first thing to do is, this function is called into a parallel region. So if we ask for OMP do, very much like this, we will probably have to explicitly say which of the value are private and which are shared. If we start quite naively, is it better if we parallelize the evaluation of the Laplacian? Okay, it's not better. So we certainly want to collapse the loops.
Sorry, what is the meaning of the two that you put after collapse?
It means that we'll collapse only two
So the
next loops.
So the two first one.
Yes, the one on the stencil is not big enough.
Okay, thank you.
Okay, so it was the do syntax in Fortran. The compiler is our friend. Okay, not better. Okay, did the compiler take into account that we are in a parallel region? So we can stuck together the parallel construct and the do construct when we are in a okay, so we certainly have even worse. So here, in order to check that we really do things as intended, we bypass the call to Laplacian function to compute it directly, and we will also write the same structure around these nice expressions. So, as usual in Fortran, we have inserted the two loops in the order where the rightmost index is the slowest one. So the closest index is the one that is contiguous. Anybody went further on this line or still slow on OpenMP? So maybe we don't need to evaluate the full field of Laplacian and evaluate the local version of the Laplacian. It doesn't look good either. So, okay, OpenMP should be the simplest. So to provide you with an idea of what we can do with the standard parallelization on threads. So here you see the 16 cores that are at 100%. But this was with the auto-parallelization of the do concurrent with NVFortran. And it's not on 300 loops, but on 32,000, so factor 100. And as we will see next time, it's much easier than playing with all these OpenMP component, OpenMP directive. So for these 32,000 steps leading to 1,000 1000 image. So in order not to lose time in the writing to disk, I save the image in a dev shm directory, so it's only in memory. And as I also said not to write, there is almost nothing in the image file, so only computing the data took us 2 minutes elapsed on the wall clock for 17,000 seconds across 16 core. So we will see the version with do concurrent from which we've gotten this with much less effort than the OpenMP. So I will provide you later with the OpenMP solution, but okay, we have had to destroy the nice structure of the initial program. We have had to use old loops. We have had to use directive, and we went nowhere. Different display for the value of this diffusivity. The rounding error is not taken into account in the same way with the various versions of NVFortran. But here, this is something with NVFortran. So we have different display. Okay, so here are the image generated from the full H5 file. So these results come from last year. And once you plug the images together, the display is as follows. At 25 images per second, we have about 40 seconds of movie. And for these 40 seconds, the thread solution that we attempted took at a runtime of 2 minutes, which is 120 seconds, which means we don't simulate in real speed on the CPU, even with 16 thread. So sorry for this absolutely non-convincing simulation. With OpenMP, it looks simple, but it is not.
Can you go through all the changes that you made? Can you go through the changes that you made to make it run with the OpenMP again, so that we can see?
The version that run is based on do concurrent and auto-parallelization with NVFortran. So I can show you the version. The OpenMP attempt I made live was not working. So in the working version, okay, you find the same module precision, the grace code settings. We have the same stencil, the same name list. You find memory file system saving of the image. Okay, here is the main routine called evolve. It first execute a single do concurrent loop, collapsing the loop on I on J, so only one loop. It computes this Laplacian as the sum of the stencil time some excerpt of the field U0, and then it computes U1. So here we have kept all the expression with their nice ways. We have only one loop surrounding all this. We have replaced those loops with a single line. And yet, NVFortran manages to extract the power of concurrency with multithread. So something we could afford to do to change this small kernel related to the initial version was also to have two steps at a time. The first step, we put the result of evolving U0, V0 to U1, V1. And instead of spending time to recopy U1, V1 to U0, V0 for the next loop, we have the second kernel that does the same thing in reverse. So you see, this kernel and the following are the same when you reverse U0, U1 and V0, V1. Okay, so this is the source code that is in the directory, in the repository, that is working with auto-parallelization of do concurrent. We should have started with this. In some older version of the evolve subroutine, we had the explicit do loops at each level. No sum, no high-level functions, but this old expression will not be seen by the auto-concurrency, the NVFortran auto-parallelization. Okay, so the CPU part has not been convincing. You will be flabbergasted by the GPU part.